So now that we have learnt about the various processes by which ionization happens and then the various stages by which dielectric goes to break down when a uniform electric field is applied across it, let us look at the various physical processes by which breakdown occurs in gases. Now, of the two most important theories which attempt to explain breakdown mechanisms in gases in uniform fields, gases in uniform fields, the first one is the Townsend theory of mechanism. Now, let us look at the circuit. I have an external supply which is providing an external applied field across a gap distance. This gap distance is filled with some kind of a gas. We are not bothered about what kind of gas. At the cathode, there are a number of primary electrons available. Where would primary electrons are like free electrons which are randomly moving around, which were already present in the gas or have appeared in between the electrodes in the gap. And where would they come from? They can come from random sources. Normally, in any gap distance, if you have a gas, some random free electrons will be available, maybe from cosmic rays, maybe from other sources. So let us assume that there are a certain number of primary electrons, let us say n0 number of primary electrons, which are available at the cathode. Now, when I apply the external electric field capital E, these electrons will be accelerated by the external applied electric field and they will move towards the anode. As they move towards the anode, they will collide with the neutral gas particles, gas molecules, and will cause ionization, resulting in the production of another electron and a positive ion. Of course, we have learned that there are various kinds of ionizing collisions which are possible. We will assume here that every primary electron results in the production of one more electron and a positive ion. So that means from the cathode, let's say one electron begins, it gives rise to two electrons through collision. Each of these electrons will give rise to two each, and so on and so forth, so that the number of electrons will continuously multiply. At a distance x from the cathode, the number of electrons, let us say, is nx. If that is the case, then we can write this equation del nx del x, which gives me the rate of change of the number of electrons with the distance from the cathode x. Del nx del x is equal to alpha nx. What is alpha? Alpha is Townsend's first ionization coefficient, and it may be defined as the net number of ionizing collisions per electron per unit distance traveled in the electrode gap. So as every electron moves in the direction of the electric field from the cathode to the anode, it causes alpha number of ionizing collisions per unit length of travel. Integrating this, I have nx is equal to n0 e to the power alpha x. At the anode, where x is equal to d, nd is equal to n0 e to the power alpha d, which gives me the result that there would therefore be an average current in the gap due to this nd number of electrons moving through the gap distance. I is equal to I0 e to the power alpha t. This is the current which is available only due to primary collisions. However, apart from these primary electrons which move through the gap distance causing ionizing collisions, there will be electrons which are available due to secondary processes. What are these secondary processes? The secondary processes include positive ion bombardment on the cathode, photoionization, detachment. Every collision that happens, every ionizing collision that happens within the gap distance, within the electrode gap, will result in the production of an electron which will move towards the anode. It will also result in the production of a positive ion which will move towards the cathode. And these ions, these positive ions, will also be accelerated by the electric field, external electric field, and they may strike the cathode with considerable momentum. As a result, they may cause secondary electron emission from the cathode. There might be other processes by which secondary electrons might be produced. We will club them all together and assume that all these processes by which secondary electrons are produced in the electrode gap can be clubbed together as an effective number of secondary electrons available at the cathode. Which brings us to, so let us say that the number of electrons produced at the cathode per second is Ns. Initially we had N0 number of positive primary electrons. Now we have on top of that Ns number of secondary electrons. As these Ns plus N0 number of electrons, total number of electrons, move through the gap distance, they will cause ionizing collisions in the manner that we have discussed in the previous slide, which ionizing collisions are determined by the first ionization coefficient alpha. So earlier we had estimated Nd, the total number of electrons reaching the anode per second, Nd, to be equal to Nd equal to N0 e to the power alpha d. We now know that N0 is now not the number that is leaving the cathode, but N0 plus Ns is the total number of electrons which are leaving the cathode. So therefore Nd can be better written as N0 plus Ns, the whole thing, in e to the power alpha t. Now, what is the number of secondary electrons? We know that the number of primary electrons at the cathode is N0, number of electrons at the anode is Nd. So, the number of electrons that's left the cathode is Nd plus Ns, and these resulted in secondary electrons being produced. This resulted in ionizing collisions through the gap. That many ionizing collisions resulted in the increase in the number of the total electrons to Nd at the anode. At the same time, the same number, Nd minus the number of electrons from the cathode, which is N0 plus Ns, the difference between these two quantities, Nd and N0 Ns, is the number of electrons produced due to collision in the gap. It is also the number of positive ions which are produced, which will arrive at the cathode. Each of these positive ions will cause secondary emissions to be produced at the cathode, and each positive ion produces gamma. So Ns number of electrons will produce gamma into the difference between the Nd and N0 plus Ns. So Ns, the number of secondary electrons at the cathode, is equal to gamma into the number of ionizing collisions, which is Nd minus N0 minus Ns. So clubbing these two equations together, we have this expression for Nd, which is equal to N0 e to the power alpha t divided by 1 minus gamma e to the power alpha t minus 1, which gives us an average current of It equal to I0 e to the power alpha t, 1 minus gamma e to the power alpha t minus 1. So now we have revised our estimate of the number of electrons available at the anode, and it now depends on both alpha and gamma, the first and second ionization coefficients. What is the condition to be satisfied at breakdown? If this Townsend process leads to breakdown, the average current through the gap distance will tend to infinity. The average current is given by ID, and this current will go to infinity if the denominator goes to 0, which means at breakdown I equal to infinity, and therefore the denominator is equal to 0, which means gamma e to the power alpha t minus 1 equal to 1. Now e to the power alpha t is much larger than 1, so therefore we can approximate this as e to the power gamma into e to the power alpha t equal to 1. So this is Townsend's breakdown criteria. The Townsend's mechanism can lead to breakdown if this particular condition is satisfied, depending upon the value of gamma, depending upon the value of alpha, and the gap distance. At breakdown, the current is infinity. However, it will not reach infinite values because the current will be limited by the resistance in the external circuit. The resistance of the external circuit will make sure that we don't have horrendous quantities of current. In fact, when we conduct breakdown tests in the laboratory, the equipment is programmed such that as soon as the current exceeds a certain value, the source trips so that we don't have a dangerous situation where too much current can lead to fire. And in the field, of course, we have circuit breakers and other things so that we do not have a very large quantity of current.